All right. Well, we are in the middle of week 2, just kind of plugging along. And up to this point, we've now talked about collisions and momentum, and we started getting a feel for what's going on with rotation. Have you guys gotten in and started working on the chapter 10 at homework at all?
Honestly, no.
No? Okay. No, that's cool. Is everybody pretty much in that same boat?
Yeah.
Yeah. Okay. So hopefully, though, when you do get into chapter 10, you're going to start seeing that it's very similar to what you did in first quarter. It's just now we're dealing with rotation. And so we're going to continue that discussion today. We're going to kind of, my hope is that we wrap up the talk of rotational stuff today. We'll kind of see how things play out. But we have a few more quantities that we need to look at and describe, but they're actually very similar to the ones that we saw in first quarter when we were dealing with linear quantities. So like always, I'm going to kind of start with a little review. So I'm going to switch to the board. And what I'm going to put up here are the quantities that we've seen so far and their kind of their relationship to the other things that we have. So again, we got theta as our angle, right? So when we've got something that's rotating, we really keep track of how far it's gone rotationally, which is going to be an angle. So then we had omega, so that was our angular velocity. So that's how quickly does that angle change with time. We had alpha, which was an angular acceleration. And so that's how is the angular velocity changing. We had I, which was the moment of inertia. And it plays the role of mass. It's really describing how hard is it to get something to rotate, to basically change its rotation. So that was I. And then most recently, last time we saw this guy tau, which was the torque. And torque is the equivalent of force. So when we have forces, that causes linear acceleration, and torques, those are the things that cause angular acceleration. So these are equivalent to X, V, A, M, and F. And so we saw some other things with this, like we've got Newton's second law. And in the case of angular stuff, instead of F equaling ma, we have tau, so torque, equals I times alpha. So if we want to find out how much we have, what kind of angular acceleration we have to look at the different torques and then figure out the moment of inertia and divide by that. All right, so we had Newton's second law. We also have rotational kinetic energy. And for that one, the kinetic energy is 1/2 I omega squared. So instead of 1/2 mv squared, we've got 1/2 I omega squared. So there was our angular kinetic energy. So again, notice how all of these things look exactly like they did for linear. It's just these are angular quantities. So a couple more things I want to bring up, just along the lines of how torque and everything works. Remember that torque is found by looking at the force that's being applied and also where that force is, where the force is being applied, and in what direction it's being applied. So with torque, it is a vector, and we saw that it was a cross product, where we have to cross the moment arm. So that's from the axis of rotation to where the force is being applied. That's what that R is. and then F is our force. So we take the cross product of those. In terms of the magnitude of torque is the magnitude of these two. So if we know how strong the force is and how far away it is, we multiply those together. But it also depends upon the angle between those two vectors. So we get the most torque if they're perpendicular. If they're perpendicular, sine of theta is equal to 1, and we get the greatest amount of torque. So if you're ever trying to turn something and you're applying a force, you want to apply that force perpendicularly. A great example is like with a wrench. So let me bring you to me so I can kind of show you what I mean. So let's say we have a wrench that we're trying to rotate like a nut or something, right? So we're trying to rotate it. So a couple things, and you can definitely see this with torque. First, you're going to want to reach out as far as possible onto that wrench. You're going to try to apply your force out on the edge to get the greatest amount of turn. We're increasing our R, right? R is from the axis of rotation, so the pivot point. So think about the nut that we're trying to undo or the screw or whatever it is, to the point where we're applying the force. And so we usually try to go out as far as possible, right? This is why levers work. When you think about levers at all, when you're trying to open a can, right, or a beer bottle or whatever, we tend to want to have a longer lever to get more torque. And then when you think about the force, like think about I don't know if you've ever had to change your tire, right? You get a flat tire and you got to change it. And sometimes those lug nuts are super, super tight. So you get on the end of that tire iron and you're trying to push it. And then you put all your weight, but you aim straight down, like you get it horizontal and you lean with all your might on the very end. That way our force is going perpendicular. That gives us our greatest amount of turn. Or with that wrench example, so you get it turning a little bit, then we reset it so that we can apply that force more perpendicular, right? And so that's exactly why torque does what it does. That's why that formula is a cross product and where all those pieces come in. So the next time you're turning anything, think about all the times you've ever had to turn something, rotate something. Keep this in mind and you can really see why torque has to be constructed the way that it is. All right, so that's kind of where we are. So now what about where we're going? Well, we now have force. We've talked a little bit about energy. So if we're going to continue this idea, we probably need to talk about work. We need to talk about power. And then if we've got motion, the other thing that we need to talk about now is momentum, right? Because we saw that there was linear momentum. The question is there going to be angular? All right, so Victor just put in the chat. He said, does theta equal the inverse sine of torque divided by R dotted with F, or R times F? Yes, you could go ahead and use that to find the angle between the two vectors, but I wouldn't recommend it because this one's kind of a more complicated formula, but you could use that. I would use the dot product. The dot product's a little bit easier in terms of finding the angle, but yes, you could go ahead and solve this for theta. Just realize that when you use inverse sine, you're going to get only the angle that's between 0 and 90 degrees, which may not actually be the angle that you have. You might have this supplementary angle, the one that's in the second quadrant, that you'd have to do 180 degrees minus that. So that's the only word of warning with that. But yes, Victor, you could definitely do that. All right, let me go back to the board. And now let's talk a little bit more about energy and work and this angular momentum idea and all that. So hopefully you remember how you find work. If we go back to good old linear quantities, work was equal to force dotted with displacement. Okay, well that was for linear quantities, and now we don't have linear quantities. So the question is, what do we get if these are angular? Well, let's draw a picture of something rotating. Let's put the force on there, and let's sort of translate this. So here's something that's rotating, which is going to make it a circle. And let's say we've got this point right here, and we're going to apply a force. Okay, so there's our force. Now, there's going to be a equivalent torque that's leading to our rotation. And if we want to know the torque, what else would we have to know? What else do we have to know in order to calculate the torque from this force? So Victor just typed in R. We definitely need to know how far away it is from the axis of rotation. So let's say that's our axis of rotation. So this would be our R vector. So there's R. So now, in terms of the work done, it's going to be the force times the distance that we travel. So this particle is going to travel a distance, but it's going to travel a distance on the arc, on the curve. And so the distance traveled is going to be our S, which is going to be R times theta. So if we know what that theta is, that's going to be R times theta. So we could rewrite this, and let's go differential. Let's go really, really, really tiny. This little chunk of work, so little dW, it's going to be the force. We're just going to keep that as a constant force. But then we need a little differential distance. Well, R is fixed, so it's just going to be R. But theta is going to be just a teeny tiny d theta. So if we sweep through just a tiny rotation, that's going to give us our little chunk of work. All right, well, this right here, F times R, that's going to be our torque because of the fact that I'm applying this force tangentially, right? I'm thinking about this as the tangential portion of this force. So these things are at a right angle, which means according to that formula for torque, that sine of theta bit is going to be 1. So the little incremental piece of work, it's actually just going to be the torque times the little tiny angle that we go through. Well, if that's the little bit of work, if we want the total work, we just have to integrate. And so for angular quantities, we find out that the work is the integral, and I'm going to put here theta initial to theta final, so from wherever to wherever as we're rotating, of torque d theta. So that's how we're going to actually calculate the work if we have a non-constant torque. If it's constant torque, this is easy, because if the torque is constant, you can pull that out, and we have the integral of theta from initial to final, and it's just the change in theta. Now, if this looks familiar, it should, because when we did work linearly, and you went to the, well, let's just look at little differential distances, excuse me, this was the integral from some initial position to some final position of f dx. So does that look familiar? Kind of remember that?
Yeah.
Yeah. So again, do the direct translation. Now, instead of x's, instead of linear positions, we care about angles. Instead of forces, we now have torques. And you can see that this is yet another example of where it's exactly the same. We're just translating to this rotational bit. So if we have constant torque, super easy. It's just torque times the change in angle. If it's not constant torque, we just put it into this kind of formula and we integrate. All right, so this is torque doing work on a rotating body. But of course, work then is a change in energy, right? That's our change in kinetic energy. And so we can have the same kinetic energy work theorem. And this is actually where that I omega squared, you can really see that pop up other than using the kinetic energy formula. Excuse me. So think about this. Instead of torque, let's write torque as I alpha. That's Newton's second law in the rotational form. So we've got torque is equal to I times alpha. So work then is going to be the integral of I times alpha d theta. But let's look at alpha. Alpha is actually a change in omega. So I can write this as I times d omega dt. And we got our theta. But let me rewrite this. I'm going to write this as d theta dt times d omega. And now d theta dt, the change in angle with time, that's just omega. So I'm just going back to the quantities and replacing them. But now if we assume that we have a constant moment of inertia, which is a pretty good assumption, the only way that that would change is if the size or mass distribution changed. And for most objects that are rotating, that's not going to be the case, right? Like when I take a ball and I spin it, that ball isn't changing its mass distribution. But it could happen. A good example, I can't do it right now because my water bottle's empty. Actually, hold on. I got a little bit. I'm going to go back to the other screen real quick. Okay, so I've got a water bottle. And this water bottle has a little bit of water in it, not a lot, but a little bit. And I don't know if anybody's tried to spin a water bottle. I imagine most of you probably have because you're of that age where like the bottle flipping is a thing. I don't get it. My kids like to do it, used to like to do it, so you guys may have as well. But think about when you spin this. If I spin it, and I don't know that we're going to be able to see it with this kind of distance, maybe I'll use my other camera and see if I can make you see it. But if I start it rotating, you're going to see that the rate at which it rotates is going to change. It's actually going to get altered because of the fact that it's moment of inertia change. So come with me. I'm going to switch to my other phone. All right, so we're just going to take a little bit of a walk. Not far, I just need a little bit of space here. Okay, so what I'm going to do, like I said, I'm going to spin the water bottle. And we're going to see if we can see a difference in the rotation. Hold on one second. I'm going to switch cameras. So now you can see me. I'm far in the background, right? So what I'm going to do is I'm going to spin the water bottle. Okay, I'm just going to let it go and I'm going to spin it like that. But what I want to see is, does the rate of spin change? Does the rate of spin change as I do this? So let's see. I don't know if you could see it. Could you see it at all?
No, there's a glare.
No, there's too much glare. That's probably too dark. All right, well, I don't know if this is going to work.
I think I get what you're trying to say though, because I mean, we have done this, or at least I have, and I can see that the bottle kind of like struggles when it flips, like if it has a little bit of water.
Yeah, so what you'll notice is as that water shifts, as you're spinning it, the water's going to shift a little bit. And that shifting of the water changes the distribution. It changes the distribution of the mass. And as soon as that mass gets redistributed in a different way, it makes it so that the moment of inertia changes. And then the moment of inertia changing changes all the angular quantities. So you can definitely see this happen when you're trying to spin something that has fluid in it, because it will readjust it. So Max, I didn't quite catch what you said because I was changing earbuds. You said you had an example of where you'd seen this before?
I was just saying, like, when we do the, I mean, because I have done the water, like the bottle flip challenge and stuff like that, where like you just flip it. And I can see that when it has a little bit of water in it, it kind of like struggles to keep like flipping. It does some weird movements. So yeah, I was just saying like
there's like a lag time, like almost a deceleration or something once the water hits it like a certain point.
Yeah. And again, we can describe this exactly with these quantities that we're talking about. You change the mass distribution, so you change I. I is your ability to rotate. So now all of a sudden it was rotating faster. The I switches, because usually what happens is you'll notice that it slows down its rotation. You start it spinning faster and then it slows down. And what happens as it spins, that water gets thrown out to one of the edges because it's feeling that centripetal acceleration, right? As this is spinning around in a circle, things inside it want to keep going out. And it's the edges of this container that are catching it. So what it really looks like is the water migrates to either side. That then is taking all this mass from the center, moving it further out. And remember, a moment of inertia is, we have an mr squared for each little chunk. So we're going from, say, r equals 0 to r equaling not 0. That increases our moment of inertia. Well, bigger I means smaller alpha for the same amount of torque, right? And so we're decreasing the ability of it to rotate, and that's why it slows down. We'll talk more about that, how changing I changes your omega in just a little bit. But we see this happen out in the real world. So my point, I guess, what I was talking about back here was that I isn't always constant, right? But when it is, then it turns out that this formula, check out what happens. So we had the integral of I times omega. So if I is constant, we can pull that out. And then we need to integrate omega. Well, that becomes omega squared over 2. And if that looks familiar, it should, because that's our kinetic energy formula, 1/2 omega squared. So work is the change in kinetic energy, which I've not proven anything new to you because this was the same thing that you saw with linear quantities. It's just now it's the same for angular quantities. All right, so there's our work. It's just going to be the change in kinetic energy. So that's another way you can think about it. So we're going to write up here, work is equal to change in kinetic energy. And I'm even going to put a little ROT below it so that we know that's rotational, even though that should be pretty obvious from the context since we're dealing with I's and alphas.
I have a quick question.
Sure, go for it, Bradley.
So say you're at the beach and you fill a bucket of water.
Yep.
And you like twirl it around and the water sticks inside of it.
Mm-hmm.
Is that a combination of angular acceleration and gravity, or what's causing the water to stay in the bucket?
Okay, so that one, think about if we weren't spinning, right? If this is my bucket of water and I'm not spinning it, I just hold it upside down, what's going to happen?
It's gonna spill.
Right. Obviously, the water's going to come out, right? Let me get my last little bit of water so I don't spill stuff everywhere. So, right, water's going to fall out. And you may have even seen a couple of drops fall out. I don't know, but it definitely happened. Got me a little wet. All right. So normally, if all we did was take that bucket and turn it upside down, all the water's going to fall out. Okay, but we're not just turning it upside down. We're spinning it, right? So if we're spinning it, what we're going to have then is some centripetal acceleration. Remember the centripetal acceleration, its magnitude is v squared over r. So the r in this case is going to be like the depth of our bucket. Oh yeah, and this is for you, Bradley, too. You noticed the cup, right?
I did notice that.
So this is going to be our r, but then we're spinning it, so we're giving it some v. So as v gets bigger, that angular or that centripetal acceleration gets greater. Now, centripetal acceleration, remember what that is. That's this thing, this cup, trying to pull itself in. The water inside is kind of free to slosh back and forth. It just wants to keep moving. So now go to Newton's second law, or not second, sorry, first law. Newton's first law says, in the absence of an external force, then your object is going to keep doing what it's doing. So think about water. If there was no bottom to this, that water is going to want to move out. Because as it's spinning, it's going in a circle, so it's kind of moving tangent, and it's just going to want to escape. But what's happening is the cup is pushing back on it and holding it in. That's what's keeping the water from flying out when it's at the top. It's moving fast enough that the water wants to keep moving upward. And it's wanting to move upward enough that it's fighting gravity, but it doesn't end up going anywhere because the top, or I guess the bottom in this case, now that it's upside down, is trying to hold it in. So this is why you actually have to spin it fast enough for it not to fall out, right? If you've got that bucket and you just very slowly rotate it, water's still going to come out because you haven't increased the centripetal acceleration enough. So you have to be spinning at a certain speed, and that's where that v squared over r comes in. Also, r matters. This is a lot harder to do depending upon how big your radius is. So it's a lot harder to do with big radius, right? If you've got just a little bucket or a little cup, it's easy to spin that and keep the water in, right? Like this one would not be that hard because it's not that large. But if I were to make this a bigger bucket, I'd actually have to spin it faster. I'd have to increase my V to counteract that R so that it would stay in. So is that a decent enough explanation for you, Bradley?
That's probably as good as you're going to get. So yeah.
Okay, well, thank you. It's as good as I'm going to give you, I think. It's really where that comes in. All right, so cool. All right, so work then, in this case, is going to be the change in the kinetic energy. So this then naturally leads us to go to power. Do you guys remember what power is, how that's defined?
Isn't it the amount of work over time?
It is work per time. That's exactly right. So in this case, if we want to find our power, it's still going to be a dW dt. It's the change in work with the change in time. Okay, well, let's see if we can kind of figure out what this is going to look like in terms of the rotational quantities. So remember our work, we define this as the torque times d theta. So that was our little differential bit of work, was torque times the little differential chunk of theta. That was the picture I drew with the circle and everything. So that's still going to be dt. Well, do the same kind of trick that we just pulled a minute ago, where we've got a d theta dt. That actually is omega. So if we want to look at power, power in the angular world, it's just a product of the torque we're applying and the angular velocity. And again, I don't know if you remember this from linear quantities, but you saw that back then power was force times velocity. If you don't remember that, you can go back and you can look at an earlier chapter and you'll see that. So yet another example of exactly the same thing, yet again. And this is one of the reasons why I do like rotation. And I think I mentioned this, is we're not really learning anything new. We're just applying it to something that's rotating instead of something that's moving linearly. So we have all the same formulas. We just have to be looking at angles instead of positions. All right, so there's our work, there's our power, everything is good. So the last one that we want to talk about or need to talk about is angular momentum. And what is that going to look like, and what does it mean? And then can we conserve it like we did linear momentum? Right, we have all those questions to ask. And then once we get that done, we'll look at combining linear motion and rotation. Basically, what happens when we have an object that rolls. Okay? But let's look at angular momentum. So obviously this is going to be related to linear momentum. So let's first go back to, do you remember linear momentum? How do you calculate momentum?
Mass times velocity.
Okay, so it's mass times velocity. Thank you. So if we go back to the linear idea, I'll just do this down here because I'm going to erase it in a second. Linear momentum, it's P, it's a vector, but we saw that it was mass times the velocity vector. All right, so if this is gonna make sense, just like everything else, let's think about a direct translation. So we're gonna need a new letter for angular momentum. I'll just tell you that we use capital L for angular momentum. Don't ask, I don't know why, but we're gonna use capital L. So that means for our angular momentum, it should be L equals. Okay, so then instead of mass, what are we going to use?
I.
Good, we're going to put in our I. So we need our moment of inertia. And then instead of V,
Omega.
that'll be our omega. So instead of linear velocity, we're going to go with angular velocity. So that is our formula for angular momentum. It's still the same idea. It's like a mass times velocity. It's just we're using the angular quantities of such. So that's what it should be if everything is good and works. And when I just said that the way it should be, you probably start thinking, uh-oh, that's not how it is. But it is. This is how it's going to work. Now I want to show a couple more of the relationships that we saw with momentum, between momentum and force and stuff like that. So you can see that it actually still works out when we go to this angular business. All right, so it's I times omega, but there are a couple other ways that we can see this. You can also get your L by taking your radial arm and crossing that with your linear momentum. So this is a lot like how we got torque from force, right? When we wanted to get torque from force, we crossed the radial arm with the force. Well, to get angular momentum, you cross the radial arm with linear momentum. So this is the same then as R crossing it with MV. And if you wanted to actually just calculate the size of this, like how much this is going to be the magnitude of R, so R, the magnitude of MV, well, that's going to be MV, and then it's going to be times the sine of the angle between them. So we can actually calculate its magnitude the same way that we did before. And so how much angular momentum we're going to get depends upon how that linear momentum relates to the R. What angle does it have as it's coming in? All right, so there's that guy. I want to show you one more thing before we play around with some examples. But another interesting thing is looking at the change in momentum with T. Do you remember what we got the linear quantity dp dt? All right, so Victor just put impulse. It's not quite right, because impulse was a force time thing. It's okay if the answer is no, you don't remember.
I don't remember.
Well, it turns out that this was force. This was another way we could actually look at the force. The force was the change in the momentum. Because where that came from, remember, momentum is m times v. So this is going to be m times dv dt. dv dt is acceleration. So mass times acceleration is force by Newton's second law.
That makes sense.
I'm sorry, what was that?
I was just saying that makes sense.
Yeah.
Hmm.
So then obviously, what should this equal if we're doing angular quantities? What takes the place of force?
Torque.
It's torque. So this is another way of figuring out your torque, is by looking at the change in angular momentum. Or alternatively, if you know the torque, you know that's a change in the angular momentum, and then you can apply that. All right, so the important ones to remember really are these, the first one, and this last one. But again, they're exactly the same as what we saw with the linear quantities, just written in angular form. So let's do an example. Let's actually calculate some angular momentum, see what kind of torque is acting on something, and so on. All right, so here's an example. Let's say we've got a jet engine. So maybe this is on an airplane. So we'll draw our airplane here. We've got our wing coming out, and then we've got the big jet engine. And if you've ever seen one of these or seen a picture of it or whatever, inside this jet engine is a big fan. That fan spins, helps draw in the air so that it can create the power. Right? This is usually the thing where in the movies somebody gets caught into it and gets all cut up to shreds. But we got this thing rotating. So here's what I'm going to tell you. I'm going to tell you the moment of inertia for this fan. It's equal to 2.5 kilogram meter squared. We also know that there's a formula for the angular velocity. And this is going to be as the fan is warming up, as it's starting from rest. But the formula for this is 400 t squared. And again, the units on this are going to be radians per second. So this is saying that at the start, at 0 seconds, it's got a 0 angular velocity, so it's not spinning, but it's accelerating. So at 1 second, it's now spinning at 400 radians per second. In 2 seconds, it's going 1600 radians per second, and so on and so forth. All right, so here are my questions. So the first one is going to be, what's the angular momentum so I want to know the angular momentum of the fan, and I'm going to put here as a function of t. Because it's going to change. As time goes on, the angular momentum is going to be different. And you should all be okay with that. Because omega is changing, and if omega is changing, then so is the moment of inertia. Or not moment of inertia, sorry, the angular momentum. Okay. So I want to know that. And then after that, let's look at what is L at a specific time. So we'll do, what is L when t is equal to 3? So at 3 seconds, what's its angular momentum? And then the last question is going to be, what is the instantaneous torque at t equals 3? So also at 3 seconds, there's going to be a torque, and I want to know what it is. All right, so let's see what we can do here. So first things first, let's find angular momentum. So angular momentum, L, is equal to I times omega, mass times velocity. So in angular quantities, it's I and omega. So I was 2.5. Omega is 400 t squared. So this is going to be 1,000 t squared. So the second part of this question then, which what is L at t equals 3? So after 3 seconds, the angular momentum is up to 9,000. Ooh, 9,000 watts. We never did write down what the units were for L. Can you figure them out?
So I was kilograms times meters.
It was kilograms times meters squared. So let me erase this because we already answered these parts. But maybe that was an mr squared. So this is kilograms times meters squared. All right, so that one was kilogram meter squared. What about omega? So Ian just threw out an answer that is going to be correct, because then omega, this is radians per second. And remember, the radians we don't really care about because they're dimensionless. So if we multiply these together, we get kilogram meter squared per second. So that's our units on this. It's 9,000 kilogram meter squared per second.
But if we plug in 3 seconds and square it, that's going to cancel out our seconds on the bottom. And wouldn't it be left on the top?
Okay, except for this 400, the units on that are actually a meter squared per second cubed. Go back to just the beginning here. It's I times omega. That's what you want to use to try to create these. Because when you have a formula like this where it's in terms of some other variable, the coefficients on it get funky units to try to account for that. So even though I didn't write it up there, when I put the 400 t squared, that 400 is really a radians per cubic second. So that then when we multiply by seconds squared, gives us radians per second.
Okay, I see that now because you square it beforehand.
Correct.
Okay.
All right, so there's our formula for the angular momentum in general. This is our angular momentum at 3 seconds. So now let's see if we can figure out our torque. So I want to know the instantaneous torque at t equals 3 seconds. All right, well, this is where we're going to go back to that idea that I just showed you a second ago about how we get torque. That torque is a change in the momentum. So for part C here, we know that torque is going to be the derivative of L. We already have L as a function of T, so we can go ahead and differentiate that. We're going to get 2000 T. So at 3 seconds, we go ahead and plug that in. We get the torque of 3 is 6,000. And you remember what the units of torque were? As he hears the crickets.
Wasn't it like
Okay, so Ian just threw out Newton meters. It is Newton meters. Remember how we find it? It was the radial arm length times the force that was being applied. So that's why it's meters and newtons. So it's Newton meters, just like joules, but not. You don't want to use joules for torque, even though they're equivalent. Okay, so I just want you to get an idea of how big that number is. So imagine that we had a lever that was 1 meter long. So think about a meter stick. And then we go and we apply a force of 6,000 newtons over there on the end of that stick. That's what this torque really is like. So that would be like having 600 kilogram mass hanging out over there. 600 kilograms is an incredible amount of weight. So this is an incredible amount of torque, but it's because this thing spins so quickly. And if you actually look at the jet engine fans, they are spinning at incredible rates, which is why they have so much torque. All right, so any questions on this example? All right, well, let's take a real quick break. I need to go grab some water real fast. So I'm going to pause the recording. All right. Okay, so angular momentum is really kind of the same idea as linear momentum. And when we think about linear momentum, remember, we can have something really small but moving quickly can have a lot of momentum, or we'd have something really large that's moving slowly could have a large linear momentum. Same kind of thing with rotational. So think about angular momentum. It's moment of inertia times angular velocity. So we could have a really large angular momentum by doing one of two things: either rotating the object very quickly, so we've got a huge omega, or we could increase the linear momentum by having a larger I, having an object that's much more resistant to changes in rotation. So it could be much heavier, right? We could have more mass. It could be larger, bigger R. Okay, so you can actually get huge angular momentum by adjusting one of those two things. And just like linear momentum, think about what linear momentum is. It's really like how, kind of a measure, not exactly, but it's kind of a measure of how hard it is to stop something, right? If something's got big linear momentum, it's hard to stop it. Whether it's a huge train that's going very slowly or a small bullet going very fast, it's tough to stop it. So angular momentum is kind of the same idea, except with rotation. So big angular momentum means it's hard to stop it rotating. So you can think of things that you've experienced in your life that spin, and some of them are really easy to stop. Like, think about like a pinwheel, right? Something you just blow into and spin. Those are usually really easy to stop rotating, right? But then imagine you've got some huge, well, take for example the fan that we were talking about, the blades of the fan in the jet engine. That's going to have huge linear momentum, which means it's going to be really hard to stop it, right? So it's really playing the same role as linear momentum, just in terms of rotation. But also, just like linear momentum, angular momentum is also conserved. So you remember what it means when we say that linear momentum is conserved? Thumbs up? Maybe? No?
Yeah.
Yeah. Okay, I'm getting a couple of thumbs up. So basically what that's saying is that in a closed system, right, when we've got a system, in the absence of external forces, the amount of momentum we have is how much momentum we have, right? It's that pile of cash. It can get redistributed, but it's what it is. So that when we have a collision or something, there can be momentum transferred from one thing to another, but it's always the same amount. Okay, but that, again, it's for a system. The momentum of a system is conserved if there are no external forces. So when we go to angular momentum, it's the same idea. It's going to be a system. We talk about the angular momentum of a system, and it's going to be in the absence of external torque. Okay, so let me go ahead and write this down. So if there's no external torque, then the angular momentum of the system is conserved. And we already saw that torque is your change in angular momentum. So that's why if there's no external torque, there's not going to be any change in the angular momentum, and therefore the system is conserved. Now, when we did angular or linear momentum conservation, it was usually in the context of collisions. And that's not going to be the case here so much. This is going to be more the rotation changes because of something happening. Let me give you some specific examples of where you've seen this before. If you've ever watched someone like a figure skater and they start spinning, a lot of times, especially near the end of their routine, they like to change the positioning of their body so that they start spinning faster, right? They speed up, they spin really fast, and then they stop. Right? But they start spinning slowly, and then it goes faster and faster and faster. Have you ever noticed what they do with their body?
They get in closer.
Okay, yeah, they bring their arms in, right? They're spinning, they bring their arms in. It's usually up above their head, but they're bringing their arms in. Now I want you to think about what that's doing. Okay, so you can take like my body, the trunk of my body. We don't like if I'm figure skating and I'm doing this, I'm not really changing the trunk of my body, you know, my chest, my stomach, and all that. But what I am doing is I'm bringing my arms in. Now think about my fist. When my arm is extended, all the mass in my fist is, well, it's about a meter away from me, right, from my center. It's a little bit under because your arm span, just in case you, I don't know if you know this, but if you stick your arms out from fingertip to fingertip is about the same as your height. It's really, really close. So for me, tip of finger to tip of finger is just over 6 feet, so roughly 2 meters. But so let's just say it's a meter. So I brought the mass of my fist from a meter away from the axis of rotation. If I bring it here, now it's only, let's say, a quarter meter away. I've really decreased that R. And when we go to calculate moment of inertia, remember it's mr squared. So that mass chunk, I just decreased its R by a factor of 4, which means I changed that moment of inertia by a factor of 16, at least the part from my fist. And similarly, like if I bring all my arm up, all of these pieces, this chunk came in, my elbow came in, my wrist came in, my fist came in, all that came in much closer. And so I've really decreased that moment of inertia. So Ralph, real quick, so you said it lowers the radius, yep. So to compensate for it, speed increases to preserve momentum. Yeah, and when we talk about the speed increases, it's the omega that increases. So when this figure skater, like if I'm doing this, I figure skater, I bring all that mass in, and especially if they put it over their heads, think about that even. Now, if your arm is pretty much straight up, and let's say the axis of rotation is going right through the center of my body, all of this is much closer to that angle or axis of rotation. And if I even get them directly over my head, I've brought that down to 0. And so now all of a sudden this fist that had way out here, whatever angular momentum, when it's directly over my head, it's down to 0. Okay, so we decrease our I.
And so is also that radius originating out from the center of mass effectively?
It's radiating out from the axis of rotation.
Okay.
Which in the case of someone like who's a figure skater, it usually is down the line that is through their center of mass.
Yeah, but you can like make those, let's say you're dancing and you want to like, you hunch over and put your arms out. They have that different spin and it may it normally slows the spin as well because you're increasing the radius.
Yeah, and that's exactly like how you contort your body can definitely change the center of mass. And people that do that, if we're going to talk about like athletics and stuff like that, obviously figure skaters, dancers, but where you really see it is like with divers. Yeah. When divers go, they really adjust the shape of their body. And by, moving their arms and legs into different tuck positions and all that, they drastically change the center of mass.
Yeah.
And can also change the axis of rotation at the same time.
And then it's like that water bottle where there's water in it. If you like change your shape in such a way that you can have like accelerating and decelerating spins, I guess.
Absolutely. Okay. Yeah. And you'll see that like with gymnasts when they realize that they were spinning too fast, for example, and they don't want to end up face planting, they'll change the location, they'll stretch themselves out or whatever to slow themselves down. And that really is this conservation of angular momentum. Because let's go back and look at the board real quick. Let me show you a formula. So if we're going to conserve angular momentum, remember that it's I times omega. So you can really think of it as I initial, omega initial is going to have to equal I final, omega final. And this we can specifically talk about where we're talking about one person, one object. So let's go back to the figure skater. So we're spinning around. We bring in the mass from our arms. We bring it closer to our body. So we decrease I. So if I goes down, in order for this to be conserved, omega is going to have to go up by a similar factor. And so like when Ralph typed in there, so to compensate for it, speed has to increase. That's exactly what happens. Your omega has to increase. And omega, that's your angular velocity. That's how fast you're spinning. So by bringing in that mass, this figure skater is making themselves spin much faster. And then Ian mentioned something about when you dance, you could, I forget, you said you like put your hip out or something. And you said that that effectively increases your R.
Yeah.
You're doing the same thing, except if you increase your R, you're increasing your moment of inertia. So now this is, I'm spinning fast and I stick my arms back out. Now if I increase I, omega is going to have to decrease accordingly. And so it's going to slow my rotation down.
I guess like a decent example of what I was trying to also say is like if you're a figure skater and you have your arms out and then you put a leg out.
Yep.
Right? Because then you get that like lopsided spin almost. It like, you know, and
yeah, you're absolutely right, because
that's not just the radius too, because then you're like, what is that? It's the same radius, but or is it more radius? Like in a cylinder, instead of it being a cone, it's like a cylinder on one side then, right? I'm trying to, or like it's half a cylinder and then a cone on one side. I'm trying to visualize it.
Okay, so let's kind of approximate a person doing this, but with more like blocky kind of pictures. And let's say that the arms are pretty much up.
Or not, now the cone is, more cylindrical further down.
Okay. I don't want you to think necessarily about the body shape itself, but think about the individual pieces and the R that they're producing from the distance. Think of R as the distance away from the axis.
Yeah, okay.
So let's say that the axis of spin is right down the middle. So when we're, let's say in the initial, we're spinning really fast. Well, let's extend ourselves out. So we start spinning like this. So our arms are out. When we bring them in, think about all the different masses, like the head, the torso, the legs, those aren't moving. So all of the little mass chunks, right? You think about them.
Yeah, we have to account for every like object.
Yep. And so we would look at each of their distance away from this axis, do that MR squared for the little differential mass, add them all up. But for these parts of the body, nothing's going to change. But what is going to change are in the arms, because let's look at this guy right here. So I'm going to make a little star for that piece of mass. Right now, it's that distance R away from the center of mass. So then we bring our arms in to try to spin faster. So there's our new arm location. Think about where that star is. That star is now here. And its distance away from the axis of rotation has decreased.
Yeah.
And it's that decrease that decreases the I, which then increases our omega. And so then what you were talking about, Ian, where we kick our leg out. So now let's say we're in this, we're spinning really fast, and then we kick our leg out. It's the same, but in reverse.
Yeah. Because
now we've got like this chunk of mass that's down by our feet. It gets swung out. And now, like, look at that. This was the initial R. It's this little tiny arrow. And now our new R is so much bigger. That causes a big increase, at least due to that chunk of mass. So when you see divers do this, if they want to spin quickly, they get their bodies tucked up into a little ball, as opposed to extending out into a pike position or something like that. So you see this all the time, but it's not usually an interaction of two objects. It's how we're changing the one object itself.
That's why I was trying to think of it like almost as center of mass, because if you curled into a ball, then the radius around the center of mass, and then it'll rotate quicker, is like what I was trying to with that.
Yeah,
Because
and
the radius along the axis is quite long, but we're spinning sideways, so it doesn't the spin is going down, let's say for a flip, instead of it going like around. Or I guess we could just see a flip is around too. Yeah, it just depends on how you're looking at it.
And really there, if you're going to look at like a someone who's doing a dive, you're kind of looking at them from the side, and this is going to really challenge my drawing ability. So this is the head, there's the arms and the legs, right? So hey, we're doing our dive. So there's your swim trunks. So the axis of rotation is probably somewhere in here, right? Because we're going to be rotating about that.
Yeah.
And if we tuck ourselves into this position, most of our mass has been brought in closer to that axis of rotation, which allows us to spin faster, as opposed to what if we start getting out of that tuck? So now you think about this, if we're still kind of going about the same place, and it may have adjusted a little bit, but most likely it's about the same. But now you notice that the mass distribution is further away from that X. Our feet are further away from it, our head's further away, and this is going to cause us to rotate less quickly. So we're going to slow down. So this is one way that the conservation of angular momentum comes into play. It just changes the rotation rate due to mass distribution because we're changing our I. But you can also get the case where there's a change in angular momentum of one object that leads to a change in angular momentum of another that's part of the system. And this is another one I guarantee you've experienced. I'm curious, has anyone ever, when they've been riding their bike, hit the brakes too hard and kind of gone over their handlebars?
No,
you know
but
what I'm talking about, right?
I hit a pothole and flew over.
Yeah. So you're going, you hit the brakes, and so it stops, but you continue to kind of like fold up over the handlebars. That's actually these are face planted into a wall. Oh, good Lord. So yes, it looks like many of us have had that experience where we go flying over the top. That's actually a conservation of angular momentum. And let me show you. If you haven't experienced this, I'm very happy for you. I hope you never do. But I know you've experienced the same thing in another situation, and I'll show that to you in a second. So let's look at this. Let's look at a bicycle. So there are the wheels on our bike. All right, and so then we've got our handlebars up here. And so we're riding our bike. That's one of those like really giant bikes that are outside of like Montbleu and stuff. But we're on our bike, cruising along, having a grand old time. So think about what's going on. These wheels are spinning. They're going to be spinning in that direction just because that's how we're going, right? So in terms of angular momentum, this has angular momentum. The other wheel has some angular momentum, but we do not, because we're not rotating, or well, technically we do have angular momentum about both of those, but they cancel each other out because we're kind of in the middle. But let's just think about this. So this is spinning. Now, all of a sudden we stop that front wheel. We squeeze down on our brakes really hard so that this stops. All right, now think about this. We just eliminated some clockwise rotation. But there was no external torque. Yes, there was torque applied to stop this wheel, but it's internal of the system. It's not like somebody outside came and shoved a stick in or something like that. That'd be a different story. This one, we're doing it ourselves by applying the brakes. So that means there has to be a compensation of some more clockwise rotation. Well, what ends up happening now is the bike and you get some clockwise rotation. So if we think of this chunk of the system, it's now going to want to rotate in a clockwise direction to counteract the loss of clockwise rotation of this wheel. All right, well, what does that mean to you? That means you're going over the handlebars. So for every one of you that experienced that and had that horribleness happen to you, it was all a result of conservation of angular momentum. So another place you see this, for those of you who have not experienced going over a bike, another place you see this is in a car. So I want you to think about this the next time you're in a car. You can be driving or you can be riding, either way. But I want you to pay attention to what happens to the front of the car, the hood of the car, when you come to a sudden stop, when the brakes are applied. So I don't know if you can kind of visualize this, but what will happen if this is our car, as you're moving, you apply the brakes, you'll see the front of the car, or you'll feel the front of the car dip. As I described that, are you kind of remembering that happened sometime?
Yeah, that happened to me like yesterday.
Yeah. Okay. So next time you're in a car and you're driving, just pay attention to that and notice that when you come up and you brake, you'll feel the front dip a little bit. If you brake hard, right, like all of a sudden that deer runs in front of you and you slam on the brakes, you'll really feel it, right? You'll feel yourself go forward, the linear conservation of linear momentum, but you'll also feel the front of the car kind of dip down. And it's exactly the same thing, right? Go back to that picture that I had of the bike. Well, okay, so that's our car, but now all of a sudden we're stopping those wheels from spinning. Something else needs to take into account that rotation, which is going to be the car itself, the car body. And so it's going to try to rotate to counteract. Now, because of its mass, it can't really like flip over. I mean, I guess you could if you were able to get enough angular momentum in the wheels. So those wheels are spinning enough, they're massive enough, and then you stop it quickly enough, you could actually get your car to flip up and over. All right, but the way that you guys drive, hopefully, the way you guys drive, that's not going to happen. But you will feel that front kind of dip down. And it's that same idea. That car is trying to take into account that rotation that you lost. All right, so fun story about this. I have a brother who was a police officer. He's now retired, but he was a police officer. And I like to just share with him physics every once in a while. And one time I was talking about this conservation of angular momentum, and he's like, "Oh yeah, we call that bowing to the radar." And I was like, "Wait, what?" He's like, "Oh yeah, because we'll have our radar guns pointed, and people will recognize, you know, they'll either see us or their radar detector goes or whatever, and all of a sudden you'll see the front of the car dip down, like it's bowing to us." And he said, "So they're bowing to the radar." I was like, "Oh, that is an excellent example of conservation of angular momentum." And again, it's something that we see all the time, that by changing the momentum of one object, it has to be taken into account somewhere else. All right. Okay, so then Victor says, so that's why there are brakes on the four wheels to cancel the momentum. Actually, no, it makes it even worse. If all the wheels stop, now we've got all the angular momentum from each one of those four are lost. And so it's even worse than just one of them. The reason that we actually have brakes on all four is to get a little bit more consistent of a braking. It's also less damaging to the individual brakes and less wear. And it does help a little bit with it because like when the back wheels brake, so when the front wheels brake, it would cause the whole thing to flip over like that. If the rear wheels brake, it still wants to rotate, but it's kind of bound by the front, right? The shocks of the front are keeping it from rotating. But really, it helps us control the braking. That's why it's on all four. There's not a huge advantage in terms of angular momentum. All right, so let's actually do one. Let's run some numbers because I know that it helps when we can actually do some values and see what's going on. So let's go to the board and we'll do an example of a conservation of angular momentum. All right, so here's what we're going to do. We're going to have a wheel that's spinning. And it's going to be spinning on an axis that goes right down through the middle. Okay, so, and we're going to rotate this way. So let's say it's rotating counterclockwise from above. So if we're looking down on it, we see it rotating counterclockwise. All right, now what we're going to do is we're going to take another wheel. And it's also going to be rotating. Okay, it's going to be rotating with a different omega. But it's going to be rotating in the same direction. So what we've got, let me just give you some numbers here. Let's say that this bottom one weighs 4 kilograms. And this top one weighs 2 kilograms. So that's the mass of those guys. I'll also give you their sizes. So this bigger one, let's say that its radius is 0.2 meters. And the top one, we'll go with its radius is 0.1 meter. Let me also give you some omegas. Let's say that this one is rotating with an angular velocity of 50 radians per second. And this top one, let's say it's rotating much faster at 200 radians per second. So here's what we're going to do. We're going to take this top one and we're going to just set it on top of the bottom one. So that once this is done, right, this was our before picture, our after picture is going to look like this. So we still have our axis of rotation that's going through the center, but the one is sitting on top of the other. And my question is, what is the omega here? What's going to be the result of putting these together? So I guess this is sort of the idea of a collision. If you'd like, this is sort of like an inelastic collision where they come and they stick together. But let's look and see what happens to omega here. So we're going to do the same sort of thing we did with the linear momentum, which is we're going to calculate the momentums at the start. Then we'll look at the momentums at the end. And we'll see what has to happen from this. All right, so are we good with all the information? Let's see if we can figure this out.
I must have missed it, but are they spinning in the same direction?
They are spinning in the same direction. Yep, they're both spinning in a clockwise, or sorry, counterclockwise, looking at it from the top. But that's actually a really good question because it so matters, right? Because if they're going in opposite directions, then one of them will be positive, the other will be negative. and that bit will cancel each other out, right? But this is going to strictly be added together. All right, so let's go to initial and see what we've got. So in terms of the initial situation, we're going to have two angular velocities that we need to, or angular momentums we have to calculate. So let's call these guys, let's say A and B. And so let's find them individually. So the angular momentum for A, it's going to be the moment of inertia of A times its omega, right? Mass times velocity. So we've got its angular velocity, it's 200 radians per second, but we don't have its moment of inertia. So this we're going to have to calculate. But these are disks, and what we calculated a while ago is that the moment of inertia of a disk is 1/2 mr squared. So we just need to know the mass and the radius of that object, which we have. So this is going to give us 1/2 times 2 kilograms times 0.1 meters quantity squared. That's our 1/2 mr squared. So that's I. And then times omega, which is the 200. So we can go ahead and multiply those together. And I believe that this gives us 2 kilogram meter squared per second. So that's how much angular momentum this little guy has. It's 2 kilogram meter squared per second. So we're going to do the same thing for B. It's going to be its moment of inertia times its omega. Well, the moment of inertia we find the same way. We just have to use the different values. It's now 4 kilograms, and it's a radius of 0.2. But its omega is slightly smaller. It's only 50. All right, so we're going to go ahead and multiply these together. And I believe that what that gives us is 4. No.
100 times
100 times 0.04. Yeah, it's 4.
Yeah.
So that one's 4. So that means that the total at the start is 6 kilogram meter squared per second. So that's how much angular momentum we have in the system at the beginning, which means this is how much we're going to have at the end. So before we go and we figure out the omega at the end, any questions about this? We okay so far?
Good.
Thumbs up.
All right. So now let's go to the final. So in the final, let's look again at what that's going to be. So now we're in this situation where we've got the little one that's on top of the big one, like this. Okay, so for the final, we only have one object. So it's going to be L equals I times omega. So if we want to know the omega, we have to take the L and we have to divide by the I. Now the L we know. The L is going to be 6 kilogram meters per second. So the question is, what is its I?
It's the combination of both masses and distances.
Yeah, we can actually calculate the individual moments of inertia, which we did down here, and then we can combine them. So this time the I, it's going to be the IA plus IB, because they're being stuck together. So the moment of inertia for the first one, it was that 1/2 mr squared, was 0.01. So you take the 1/2 times 2 times 0.1 squared. For the second one, same story. You take your 1/2 4 times 0.2 squared. And what that ends up giving us is 0.08. So the total moment of inertia for this object, once they get put together, is 0.09. So we're going to take our 6 and divide by the 0.09. So if I did my math right, it's going to be 66.7 radians per second, but definitely check my numbers on that. I feel good about it.
You're good.
Okay. So think about how those two were spinning originally. The little one was spinning at 200 radians per second. So that one got slowed down a lot. The bottom one was rotating at 50 radians per second. So that one sped up. And there's that conservation. We had a decrease in one that was matched by an increase in the other. So this is the general kind of problem that you're going to do when you've got some sort of conservation of angular momentum. And it's just looking at how these momentums change as we go through some process like this. But it's the same as linear momentum, which is the pile of momentum money is the same. We're just redistributing. So real quick follow-up to this. What if instead of them both being rotating the same direction, what if they'd been rotating in opposite directions? So let's say that the bigger one was still rotating in a counterclockwise direction looking from above. But what if the smaller one was actually rotating the other way? What would have changed?
I think it would still be speeding up the larger one, but just at a much less of a rate.
Okay.
But
So you
it
think
would
the
still
bottom
sped
one,
up.
you think it'd now be spinning same direction as the bottom one,
Yeah,
not as fast?
correct.
Okay. And I see Victor put in the chat negative omega. And that is actually what happens here. Now this omega is going the other direction. So it's now a negative, let's say. Which means when we went and we calculated its angular momentum, this would now need to be negative. Which means our overall
It would have been 2.
would have been just 2. Well, when we go to the final, that means that we now have 2 here, because that's how much our stack of angular momentum is. What would change in this I, the 0.09?
It's going to be a little bit less.
So he thinks. So Bradley thinks a little less. Victor says nothing. If you're struggling trying to figure that out, it's because it's a trick. Nothing changed, because that I is all about just the mass distribution of the object. And when we put these things together, the mass distribution is the same. This picture still looks exactly the same with its masses and everything. So it turns out that I wouldn't change. So this number then would actually be 22.2 radians per second. So it still would be rotating in the same direction as the bigger wheel. It's just way slower. It's a third of the angular velocity that it had otherwise. And in fact, what happened was the big one slowed down. The big one had been going at 50 radians per second, but now it's decreased down to 22.2. So it had to slow down to take into account that this one basically sped up. I know you don't like the thought of that, but it really did speed up because it went from a negative to a positive. So it had to increase its angular momentum, which meant the bigger one had to decrease its angular momentum. So in terms of calculations, the calculations are pretty easy. Where you're going to run into issues are the plus and minus. They're working together versus they're working apart, right? They're countering each other. So that's going to be the challenge with these, is just making sure that you either reduce them or add them depending upon what is appropriate, right, in terms of what's going on.
As long as we know which direction both are going, it should be pretty easy though, right? It would just be like either subtracting or adding them, right?
Correct. And the fact that I made the one positive, the bigger one positive and the smaller one negative, didn't really matter. Because let's say I had reversed that. I had decided that this rotating in a clockwise direction from the top was positive. That would have made the initial for A positive. The initial for B then would have been negative, which would have given me a -2, which then if I continue through would have given me a negative omega. And the negative omega would have matched the rotation of the bigger one, and so it still would have worked out. So
I see.
Yeah, so you're right, Max, that it turns out it doesn't really matter as long as you're consistent. And it is pretty easy to look at one and go, okay, so they're going in opposite directions, so I have to take one minus the other and then go from there. All right, other questions? All right, well, let's finish up today with one more topic. We're going to look at rolling motion. And so rolling motion, this is going to be where we have to take into account both rotating and linear quantities. Because when something's rolling, like you think about a rock rolling down a hill, a bike wheel rolling down the road, something like that, there's not just rotation, but there's also lateral movement, right? There's linear motion going on as well. And so when we have rolling, we actually get both angular and linear stuff going. And so we kind of have to deal with both of them and take them both into account. So let's look at that. Let's look at what happens when we've got rotation that leads to rolling. Okay, so let me draw a picture. And to make life easy, we're just going to be rolling along level ground right now. But let's say we've got a wheel that's rolling. So I'm going to mark the center of mass with an X. But assuming that this is like a normal kind of wheel, that center mass is going to be dead center, right in the middle. And so let's think about what's going to happen as this rolls. So this entire wheel is going to be moving. Let's say we're moving here to the right. So we're going to be moving in this direction. And I'm going to say that it's got a velocity of v. And I'm going to put a little cm below it meaning to show that it's the velocity of the center of mass. All right, so this is moving, but at the same time, it's also rotating. So I'm just going to put a little arrow like that showing that it is rotating. Right? And how fast is it rotating? Well, let's just call it omega. So that's going to be the omega of this guy. So it's probably not going to surprise you that these two things are related. The omega and the VCM, the velocity that this wheel is moving, and how quickly it's rotating are going to be related. But let's kind of play with this and see what's going on, see if we can get a relationship between all these guys. So first, let's look at kinetic energy. So in this case, the kinetic energy is going to have two pieces to it. There's going to be a rotational kinetic energy, and there's also going to be a, I'm going to call it translational kinetic energy. So there's the part that's due to its spinning and the other part due to its moving. So the kinetic due to rotation, that's going to be 1/2 I omega squared. And then the part that's due to the translation is going to be 1/2 mv squared. And to be good, I should probably put the cm on that v. And I should probably also put on this I a little cm, because we're looking at the moment of inertia about the axis that goes through the center of mass. You may remember that this depends upon where we're rotating, and there was the parallel axis theorem, for example, that could calculate I's if we're about a different axis. But this one, since we're rotating about the center of mass, I'm going to go ahead and call it I center of mass. So when you've got something rolling, it's got both of these pieces. Before we go too much further, I do need to mention this. This is without slipping.
Do we ever go into slipping or no?
You can definitely do stuff with slipping. Yep.
And then friction's involved?
So friction is actually involved right now.
True.
Friction is what's causing it to roll.
Go forward, yeah.
If there was no friction, your bicycle wheel would never spin. You would just be sliding along the ice and your wheels would not be spinning. That's why it's a lot harder to get going when it's icy, right? Like think about when it's been an icy day and you're driving, you come to a stop and you have to get going and your wheels spin a little bit.
Yeah.
That's because the friction isn't there to cause the rotation. So you actually have to have the friction in order to even get any kind of rolling. So what ends up happening if you slip is there isn't a direct relationship between the omega and the V anymore. And that then was going to change the relationships here.
Okay.
Because what we're going to do, we're going to see that you can actually kind of relate these two using the wheel itself, the size of the wheel. All right, so let's kind of look at this now in terms of how omega is related to all of this. So right now, think about this wheel. Every piece of this wheel, not just the center mass, but all of it is moving to the right with the same translational velocity, the same linear velocity. So if I were to redraw that wheel, we could think that up top, there's a vector with that same V. On the bottom, right? It doesn't matter where, but every point on this wheel has the same translational velocity. So if you think about the one on the top, because this is going to be how we can relate the V and the R, right? This thing, we saw that V was equal to R times omega. And so if we think about how fast the top is spinning, which then would be how fast everything is spinning, that V is going to equal R times omega. Or another way to think about it is think about it as this wheel rotates. And let's just look at this point right here. So I'm going to call that point A. Now, after a while, we're going to get back to where A is on the bottom again. Right? That wheel is going to gone and done a full circle, and we're back down on the ground. So the question is, how far was that? Well, it's going to be the circumference of the circle. We're going to move horizontally the same distance as the circumference of the circle. Do you kind of see that? Because as we move along, think about this point right here. As we rotate, it's going to come into contact with the ground at that spot, because this linear distance is the same as this arc distance. And then a little bit later, call this one star, it's going to run into a point here where that arc length is the same as this horizontal distance. So if we're going to go all the way around, that horizontal distance has to equal the entire arc length, which is our circumference. So this thing, if we look at distance over time, right? So the velocity of the center mass, it's going to be that distance, 2 pi times the radius, over whatever that chunk of time is. Well, that 2 pi, that's actually the angle that we go around. So we could change that instead of a 2 pi, think of it just as the angle. And then theta over t, that's r omega. So it does exactly what we expect it to, that this v from our center of mass is actually equal to r omega. Anyway, all right, so this is the bit that comes from translation. Now let's look at the part due to the rotation. So now when it comes to velocity, due to the rotation, these things are going to change their direction. These are now all going to be pointing tangent to the curve. So here are a bunch of velocity vectors due to the rotation. But each one of those has a velocity that's equal to the one at the center of mass because of this calculation right here. So what we're basically doing is we're adding these together. We've got a linear set of velocities. We've got a rotating set of velocities that we combine together that are going to give us the velocities, total velocities, at any old point. So let's look at the result of this. Let's see what those vectors look like. So this is going to be our total picture. So let's start with some easy points like the top. So the top point has a horizontal translational vector, also a horizontal rotational velocity vector. They're going to add together. So what we're going to get up here is a vector that's twice as long. And this one's going to be 2 times the velocity of the center of mass. We're getting one of them from the translational and one from the rotational. So now let's think about it on the bottom. So this time we've got a right pointing translational vector, a left pointing rotational vector. So that means that they're going to counteract each other. and they're exactly the same length. So that means at the bottom, we've got V equals 0. So already this is kind of weird. Think about what this means. This means that the bottom of a wheel has no velocity. So if we're not slipping, if we're just doing rolling motion, then the bottom of a wheel isn't moving at all. And the point at the top of the wheel is actually moving twice as fast as the translational velocity. So like if you're driving your car at 60 miles an hour, that means the very tops of your wheels are actually going 120 miles an hour. And the bottom of the wheels, the part that's actually touching the road, have no velocity whatsoever. Crazy.
So does that, if you're being shot by a radar gun on the wheel, at a certain point on the wheel to like just knock you?
Okay, so luckily, I like where you're going with this one, Ian. But luckily, when you do or when you're getting shot by a radar, right, it's reflecting off of the entirety of the car. It doesn't have a small enough beam that it could actually do that. The LiDAR, the laser, the laser ones potentially could. I do know, again, from my brother who does this sort of thing or did this sort of thing, that they, with the laser ones, they always target like the license plate.
Okay.
Because
so
that's
they still do fair. They're fair.
It should be fair. I mean, as fair as any of that stuff could be. Obviously, there's going to be potential mechanical issues or user error and all that, but I don't think that they're that sneaky. Okay, I don't think they're smart enough to be that sneaky. And sure. I'm not speaking for all cops. I'm speaking for my brother. If he's a good representative, then they're not smart enough to figure that out. But yeah, it turns out that it is a little bit crazy that parts of your vehicle are actually going faster, and specifically the top of your wheel, it's going twice the velocity that you have, that your speedometer is reading.
Yeah.
Kind of crazy. Okay, so there's top and bottom. Now let's also look at the sides. I think the sides are pretty easy vectors to determine or to see what's going on. So let's go look at those. So let's look at the back. So remember what's going on there is we have a rightward pointing translational vector, and we have an upward pointing rotational vector. So when we add those vectors together, what we're going to get is an angle that's going at 45 degrees because they're equal magnitude. And the size of that is going to be the square root of 2 times VCM. Right, because it's just from the Pythagorean theorem on that. So that part is also actually moving faster than the car itself. It's moving at 1.1 or 1.4 something times that. But notice that not all of that is in the horizontal component. So it's moving that fast, but up towards the car. And then similarly, if we're over here on the right, the forward end, now it's got a right pointing translational and a down pointing angular. So again, it's going to be at 45 degrees with that same magnitude of square root of 2 times the VCM. So it's pretty crazy if you actually look at this, what the math tells you. And for sure, that result of the top going twice as fast, I think is the big one, because that's pretty cool.
I have a
Okay, so I'm
question.
going to see if I can pull up a picture of this.
Hey,
because it
Bruce.
is kind of interesting that you can tell that the top is moving much faster, and that the bottom is basically not moving whatsoever. So I'm going to search, just doing a Google search for some sort of an image.
Really quick, I don't know if you went over this, but why? I mean, I feel like the sides would either have to be pointing up or down, like straight up or straight down. So
So
why
you
are they?
mean the resulting vectors
Yeah,
that I have over here?
yeah,
Okay. So the reason why they're doing that, I'm still on the board, right? You guys can see that?
yeah.
Okay. So here is our, I'll call it V sub t. That's our translational vector. The rotational vector is pointing upward. So let's call that V sub r. And when you add vectors together, remember we do them head to tail. So you could just bring this VR over and think of it like that. And so just by adding those vectors together, the way that vectors work.
Yeah, actually, that makes complete sense now. I didn't realize that you were adding them both, but now I realized.
So also, Bruce, like it'd be then like on that left side, you have increasing size of vectors up to the 2, and then it's like decreasing down back down to 0.
Correct.
Okay.
Yeah. So there's no arrow here. They start, and they're always going to be pointing to the right. So like this, when we get just a little bit over to this spot, it's going to be pointing, I don't know, something like that direction, but kind of tiny. And as we move, they're going to elongate, and they're going to get more upward pointing until we get here. And then once we get past this point, they're going to start getting flatter, but longer. And then you're right. Once we reach the top and we come back around, they're going to shrink until eventually they're back down to 0. Does that answer that question, Ian?
Yeah. It just
You were
made me,
definitely,
like think of gradients, but I don't know if that has anything to do with the type of curl, or is that's not curl, but like what would that? I
yeah.
don't even,
Don't think
well,
about it as gradient.
yeah.
Don't think about it as gradient at all, because it's a completely different thing.
Yeah, it's just like an increasing and decreasing vector size.
Yeah, it's just a matter of how the vectors get put together and form that. So I'm having trouble finding a good picture of this. I know that there's a good picture of this, I think, in the book, where what you'll see is that the top is really blurry. So like if you were to look at the picture of this wheel as it's spinning, the top is going to be really, really blurry. And the bottom is going to be crystal clear in a photo because of the fact it's not moving. You can actually see this if you go out and you look at wheels that are spinning. I know there's not a lot of traffic on the road these days, but there's still people out driving. So next time you're out, go stand on the side of the road and watch people drive by, or, you know, have a friend of yours on a bike or whatever. And as they go by, concentrate on the bottom. See if you can focus on the bottom of the wheel. And you're going to see that you're able to do that. Then try to focus at the top of the wheel, and you're going to notice that you can't. And that's because it's going by too quickly. I mean, think of it as like moving just, you can't concentrate enough. You can't see it well enough to focus in on the top. So not only does the math say it must be this way, but you're going to see that it must be this way when you actually go out there and look at it. So yet another one of the many things that I'm going to tell you. hey, pay attention to this and you'll see it somewhere out in the real world.
That's pretty cool.
Yeah, it is. This is for sure why I like physics, is because as you start looking at this, I mean, it's very mathematical, and I like that. Not the math itself, but the structure, right? It's really structured. It's logical progression, right? If A, then B, then C. So I like that. But not only that, it does totally explain what we see. And you can start with just a few things. Like what we're doing now is being built on what you guys did in first quarter. And if you think about the assumptions that you made in first quarter, there are very few. Right? I mean, yes, we tend to do the whole ignore air resistance and all that. But if you just go with the how we're building this, like it really comes down to, we've got Newton's laws of motion. We assume that those are true. And that's about it. Everything else falls from that. And I love that. I love, they call this an axiomatic system, where you just start with a couple of things and then you prove the rest. Math is very much like that, right? Like in geometry, you just assume a couple things and next thing you know, circles or triangles. But I love the fact that you can do a little bit of math and be able to describe exactly what we see. And the more of this you do, and the more you calculate, and then you go out and you try to look for it in the real world, the more you'll see it. And just to be real, this is how I operate. Like when I'm out in the real world, I'll see stuff all the time and I'll go, oh, cool. There's a great example of insert physics topic here. Which is why I think my kids are the way they are, right? Because I'm always pointing it out. I think it makes me a little less fun sometimes when it's like, ooh, why is the rainbow there? It's no leprechauns, right? I'll tell you exactly what it is. But it also makes things like amusement parks the best thing ever. Because when I go to an amusement park, all I think is physics. And it's great because I'll think about, okay, what did they do to design this to make you feel the way you feel? And again, that same brother, the cop brother, one time at an amusement park, we were doing one of those free fall towers, where they raise you up and then they just drop you and you free fall. And I was telling him about how everything's going to fall at the same rate. And so I took a coin out of my pocket, I think it was a dime, and I set it in my hand. And so we're all watching it and we start to drop. And now the dime is just sort of like hovering above my hand because it's falling at the same rate. And then after a little bit, all of a sudden you see it drift up and then goes flying away. Now, of course, it didn't go flying away. It just quit falling as fast because of air resistance. There was finally enough air that we could see it. And so we spent quite a bit of time talking about that. And then what was really kind of cool about this whole situation is we were watching so intently. So it was me and my brother and my son. We were watching the dime so intently that none of us got that like stomach raising into your chest kind of feeling. All those butterfly stuff were gone. And that really illustrated that, how they say mind over matter. Anyway, so that's how I live my life, which means at some point you guys keep doing this enough and keep the interest going, you'll live that way. And I think it's kind of fun because as stuff happens, you just start going, why did that happen? What's going on? And you can reason it out. Sometimes you guys ask me questions and I don't know the answer, but I'm able to kind of think about it for a second and go, oh, this has got to be what it is. And I'm just going back to the basics. So anyway, so here you go. There's rotation. It really is just like lateral. It's just we're spinning. And so now we care about changes in angle instead of changes in position or distance. So, all right, well, I'm going to hit pause.